Hello, welcome. In this lecture I am going to discuss another application of Maxwell Boltzmann distribution, that is how to calculate fraction of active molecules at a given temperature T, right, which is actually a very important expression in Arrhenius equation. So what we are going to see is that in Arrhenius equation, you might have seen this expression. Arrhenius equation is K is equal to A into e power minus A by RT. Here what is this expression? K is nothing but rate constant, and we have two terms here. One is the pre-exponential term and the other one is the exponential term. Okay, this exponential term e power minus A by RT gives fraction of active molecules present at the temperature T. Okay, what is meant by that? See, you know very well, in gas-phase reaction, collision is responsible for the reaction. Okay, so we have reactant molecules. If the energy of the reactant molecule, if it is greater or equal to EA, where EA is called activation energy, if the reactant molecule possesses at least the energy EA or above EA, then those molecules are called as active molecules. If active molecules undergo collision, yes, you will get product. Very simple. Now what we need to find out is, out of, see, so you may have a lot of molecules, right? Out of all the molecules, right, out of say for example I have n molecule in the system. Out of n molecules, how many molecules are active at temperature T? Okay, that is, say for example, if Na is the number of active molecules, then Na by n will give you fraction of active molecule present in the system. How to get this value? Right? Actually, by using Maxwell Boltzmann distribution, we can show that this is nothing but equal to this quantity e power minus A by RT. Okay, so in the Arrhenius equation, the exponential part e power minus A by RT is derived by making use of Maxwell Boltzmann distribution. This is what we are going to discuss now. Okay, yes. How to get the expression E power minus A by RT as the fraction of active molecule present at temperature T. Okay, see what I'm going to do. Let us assume we have totally n molecules in the system, n molecule, and for each molecule, using quantum mechanics, we can find the allowed or quantized energy levels. Okay, let us say these are the quantized energy level. This is the ground energy level. The energy of the ground level is 0. Let us also assume that the energy levels are non-degenerate. Okay, so this is the first level. Let the energy is E. Second level, the energy is 2E, 3E, right, etc., etc. And we have some energy. Let me write this energy as E minimum. Okay, and that minimum energy, see, let us consider this level as ith level. This is the ground level, the first exit level, second level, third level. Let us consider this level as ith level. Okay, and the energy of the ith level, I am assuming that energy is minimum energy, which is actually given as I into E. Okay, see, for this I equal to 0, for this I equal to 1. If I put I equal to 0, I will get 0. If I put I equal to 1, I will get E. If I put I equal to 2, I will get 2E. Okay, if I put I equal to, if I is I, then energy is I into E. And above this we have many levels. Okay, now what I am going to do is, suppose assume that this is the minimum energy required for the molecule to be active. Okay, E minimum is the minimum energy required for the molecule to be active. So if molecule present here are above these levels, all these molecules are active molecules. If any molecule present, okay, at least at the level E minimum or above, right? All those molecules are considered as active molecules. Now, how to get the number of active molecules present in the system? Okay, yeah. So what I'm going to do, let us say Na molecules, right? Let us say Na is the number of active molecules present at temperature T. Okay. So Na is the number of active molecules. Okay, present at temperature T. Okay, now what we need to do, we need to find out this Na by N. Na by N gives you fraction of active molecule present at temperature T. Okay, from using Maxwell Boltzmann distribution, we can write this fraction as Na by N equal to e power minus energy of the ith level by kBT whole divided by partition function Q. Okay, here we write generally energy as EI, but here see the energies are given as 0, 1E, 2E, 3E, and for ith level it is IE, right? Therefore, we can also write this as e power, instead of EI, I am going to write this as I into E by kBT by Q. Okay, where I can take value from 0, 1, 2, 3, 4, etc. If I put I equal to 0, I will get the ground state energy. If I put I equal to 1, I will get the first excited level energy, and so on. Okay, yeah. So let me take this as equation number 1. Okay, or I'll write here, and so what is that? Fraction of active molecule Na by N is equal to e power minus I E by kBT over Q. I'll take this as equation number 1. Now see here, what is partition function in the case of non-degenerate levels? Q is equal to summation e power minus I into E by kBT. Okay, where I goes from 0 to infinity, right, or up to the occupied levels. If you put I equal to 0 here, if you put I equal to 0, I'll get e power 0. E power 0 is 1. If you put I equal to 1, I'll get e power minus E by kBT. If you put I equal to 2, I'll get e power minus 2E by kBT. Then if I put I equal to 3, I'll get e power minus 3E by kBT plus etc. etc. Okay, and this I can write as 1 plus e power minus E by kBT plus e power minus E by kBT the whole square, and this I can write as e power minus E by kBT the whole cube. Okay, plus etc. etc. Okay, suppose if we take this value as x, okay, then this expression is something looks like this. Q is equal to 1 plus x square plus x cube plus etc. etc. It looks like this. Okay, and here see e power minus E by kBT, you know very well, e power minus E by kBT, okay, this value is less than 1. So whenever x is less than 1, right, whenever x is less than 1, then by using binomial expansion, okay, or using binomial function, we can write this as, this is approximately equal to 1 by 1 minus x, right? If x is less than 1, we can write this summation approximately equal to 1 by 1 minus x. Therefore, the above expression can also be written as, okay, if e power minus E by kBT is taken as x, and here also x is less than 1, therefore this summation can also be written as, right, the next page, written as q is equal to, okay, 1 by 1 minus x. In the place of x, I will put e power minus E by kBT. Right, let me take this as equation number 2. I'll introduce this equation 2 in equation 1. equation 1. Okay, so in equation 1 we have a fraction of active molecule Na by N in the left hand side equal to, in the numerator we had e power minus I E by kBt, and in the denominator we had Q. Now what's the value of Q? Q is 1 by 1 minus e power minus E by kBt. Okay, if I bring it to the numerator, I'll get e power minus I E by kBt into 1 minus e power minus E by kBt. Okay, I'll keep this, I'll take this expression as equation number 3. Okay, now let me move on to some other terms, some more terms. Say for example, okay, how to calculate the active molecules. I have told you, see, I have told you if I is equal to I minimum. What is I minimum? It is the minimum energy required for the molecule, right? If I is equal to I minimum, right, and if it goes above that, suppose if you take molecules, right, at the I minimum and above that, those molecules are called active molecule, right? So this will give you, this summation will give you number of active molecule, right, which can be obtained by using this idea, that is I equal to, you calculate from a number of molecule from I equal to 0 to infinity. Okay, then subtract number of molecule from I equal to 0 to I is equal to I minimum minus 1. Okay, I minimum is the minimum energy required for the molecule to be active. The molecule which are below, right, those molecules are inactive molecules, are not active. Okay, so this is total number of molecule. This will give you total number of molecules in the system, and this will give you number of inactive molecules. Number of inactive molecule at the temperature T. Number of inactive molecules. So if I subtract number of inactive molecules from total number of molecule, we'll get number of active molecules. Okay, and this quantity is nothing but total number of molecules, which is nothing but N. Let me write the next page. So number of active molecule equal to, okay, total number of molecule N minus this value, that is I equal to I0 to I equal to I minimum minus 1. I minimum minus 1. Okay, minus I minimum minus 1. Okay, and Ni. So this will give you number of inactive molecules. Okay, now I am going to focus on this now. You know very well, according to Maxwell Boltzmann distribution, Ni by N is equal to e power minus, in this case it is IE by kBt by Q. This we know. Or I can write Ni equal to N by Q into e power minus I E by kBt. Okay, so I'll substitute this here. Therefore, number of active molecules equal to total number of molecules minus, if I put in the place of Ni, if I put this quantity here, capital N is a constant, partition function is a constant for a given system, okay, at a given temperature, right? Therefore, you can take N by Q as N by Q out. So I can write this as summation I equal to 0 to some I minimum minus 1 into e power minus IE by kBt. Okay, now I'll keep this N as such. I'll take N as common here, N 1 by Q. Okay, and what is this summation? This summation, right, I'll focus on the summation alone separately. Okay, so let me take this as equation number, what's the running equation? Second. So running equation number is 4. So I'll take this as equation number 4. Now how to get this value? See, we have to find the sum from I equal to 0 to up to the level I minimum minus 1, e power minus I e by kBt. Okay, we need to find this sum up to I minimum minus 1. Okay, so if you put I equal to 0, I'll get 1. If you put I equal to 1, I'll get e power minus e by kBt. If you put I equal to 2, I'll get e power minus 2e by kBt, right, plus etc etc, and up to a term which is nothing but e power minus I minimum minus 1 into kBt, e by kBt. Okay, we need to find summation up to this term. It is not infinity term. Okay, it is not going to infinity. If it goes to infinity, we can use binomial expansion. Okay, but this term stops up to this level, right? So to find this summation, right, I am going to use the geometric progression. Why? Because this expression looks like this: e 1 plus e power minus e by kBt plus e power minus e by kBt the whole square plus e power minus e by kBt the whole cube, etc etc, plus this term. Okay, now see here, this is the first term and this is the second term. Second term has energy E, and this is the third term. Okay, or if you compare here, first term has energy, first term is this, second term has energy e power minus e by kBt, right, and third term has energy e power minus 2e by kBt, and fourth term has energy e power minus 3e by kBt. Therefore this term, okay, has energy I minimum minus 1 by kBt. Okay, why I am telling this? Because this expression something similar, looks similar to geometric progression, right? You know very well, in mathematics in 10th standard or 9th standard you might have seen this. If you have an expansion like this, a plus ar square plus etc etc up to ar power n minus 1. Okay, so this is the first term. First term does not have r, second term has r1, r power 1, third term has r power 2. Okay, like that we have terms up to r power n minus 1. Okay, and here a is first term, r is the common ratio. Then if r is less than 1, observe carefully, if r is less than 1, then we can write this expression, the summation, as this summation should be equal to a into 1 minus r power n by 1 minus r. Okay, this you might have seen in your 9th standard or 10th standard. Okay, for geometric progression, right, if the common ratio is less than 1, then we can take the summation, we can find the summation using this formula. Now see our expression, that is summation I0 to I minimum minus 1 e power minus IE by kBt. If you see this expression, we get the similar expression 1 plus e power minus e by kBt. In the last page we had this expression, right, e by kBt the whole square, okay, plus e power minus e by kBt the whole cube, plus etc etc. Okay, and see here, this is the first term, let me take this as a, so a equal to 1, right, and this is my second term, and this is the third term, this is the fourth term. Like that I have a term, that is nth term, which is a into r power n minus 1, so where r is e power minus e by kBt here, okay, and n minus 1, which is nothing but I minimum minus 1. Okay, so this is exactly similar, and this is nothing but r. Actually a is 1, therefore this is r. So e power minus e by kBt is nothing but r, okay, and the first term is 1 now. So what is the summation? See here, in this case, e power minus e by kBt, we all know that e power negative quantity is less than 1. Okay, so r is less than 1 in this case. If r is less than 1, then this summation should be equal to a value is 1, so 1 into 1 minus r value is e power minus e by kBt, okay, whole power r power n we should put. Listen, see, if you have terms up to n minus 1, then you should put n here, okay, you should put n. So similarly here I have I minimum minus 1, therefore I should put I minimum here, I minimum, okay. I'll remove this bracket, I'll change it for a moment, I'll keep it like this, divided by 1 minus e power minus e by kBt. Okay, you can also write this as 1 minus e power minus I minimum into e by kBt whole divided by 1 minus e power minus e by kBt. Okay, so this will give you number of inactive molecules present at temperature T. Let me substitute this in equation number 4. So what is equation number 4? Yeah, in equation number 4 we have this quantity, this number of active molecule equal to n minus n by q, okay, into that summation quantity. So now we got the value of summation. The summation value is 1 minus e power minus I minimum into e by kBt whole divided by 1 minus e power minus e by kBt. Okay, this is the value of the summation. Now if you observe carefully, n minus n by, what is q actually? Q is nothing but 1 by 1 minus e power minus e by kBt. This is as per equation number 2. Okay, you just refer after once we complete the derivation, right? As per equation number 2, q is nothing but 1 by 1 minus e power minus e by kBt into, so here we have 1 minus, okay, let me write in the bracket 1 minus e power minus I minimum into e is nothing but energy, minimum energy required. I minimum into e is nothing but e minimum by kBt divided by 1 minus e power minus e by kBt. Okay, so you can cancel this quantity and this quantity, right? So what we left with this, I'll take n as common here, n as common. So if I take n as common, here we have 1 minus, then we have 1 here, 1 into minus 1. So here we have minus 1 into 1 is minus 1, and minus of minus become plus e power minus e minimum by kBt. Okay, plus 1 minus 1 cancel. I'll bring this capital N to the left hand side. So Na by N. What is Na by N? It's nothing but fraction of active molecule present at temperature T, which is equal to e power minus e minimum by kBt. Okay, what is E minimum? It is the minimum energy required. Okay, if any molecule has energy at least E minimum or above E minimum, those molecules are active molecules. Okay, but here E minimum is the minimum energy of a level. Okay, but we normally specify the energy in joules, right? Whereas here these are all energies of individual molecules. Right, therefore to specify the energy in joule, in mole, right, in moles, so what I'm going to do, I'm going to multiply the numerator and denominator by Avogadro number. So let me do that in the next page. If I multiply the numerator and denominator by Avogadro number, so Na by N equal to e power minus, I'll multiply, so E minimum is in the numerator, I'll multiply this by Avogadro number divided by kb into T. I'll multiply the denominator also by Avogadro number into kb into T. Okay, and you know very well this energy, that is minimum energy into Avogadro number will give you energy per mole, which I am going to represent as EA. So what is EA? EA is nothing but minimum energy required, okay, for minimum energy required for a molecule to be active, and I am expressing that quantity in moles. That's all. Okay. So Na by N is equal to e power minus, this become EA by, you know very well, Avogadro number into Kb is nothing but R. So I'll get e power minus EA by RT. Okay. So this is how we get the expression e power minus EA by RT as fraction of active molecules at temperature T. Okay. So by making use of Maxwell Boltzmann distribution, right, we can find this e power minus EA by RT term, okay, and this gives you the fraction of active molecules present at temperature T. Okay. Yeah, I stop here. We'll continue with another application in the next class. Thank you.